Okay, let's talk about oscilloscopes. Now, oscilloscopes are, to kind of take it down to an elementary level, are meters for AC. Now, they do a lot more than that, but that's kind of how I want to describe them. So they're measuring something that exists. They're not changing that waveform or anything like that. We're just viewing a video or video representation of that waveform on the screen. And there's analog and digital, and they both have similar features. Digitals are a lot more advanced. They can do things much easier on that screen than we can on the analog. But this is a representation of an analog scope. Now that's the large square area right here. Now you see a little wire going between this and this item I've outlined in red down here. And this is all just a virtual box. But what we've got is the ability to use this, what we're saying is a function generator. This little narrow, thin rectangle is acting as our function generator. It creates the waveform. It is a separate piece of equipment from the oscilloscope. Now, the oscilloscope is not always measuring the output of a function generator. It may be measuring the output of some other type of device, but in this case, we have a piece of equipment in our lab called a function generator, and that's what we're using here to create this signal. So it doesn't matter where the signal comes from. The oscilloscope, which is this big device up top labeled scope, and that's what we often call them, is scopes instead of oscilloscopes, just for a little easier to say word, is actually doing the measuring of that signal. And again, throughout this particular video, I'm not going to change the output of this function generator. This value is going to remain the same throughout. So when we look, I'm creating a sine wave. I could change it to a square or a sawtooth or whatever the case might be, but we're going to deal with sine waves today. The amplitude is 2 volts, which is 4 volts peak to peak. So this 2 volts is a peak value. The 4 volts peak to peak is the negative peak and the positive peak added. So if we have an amplitude of 2 volts, a positive and 2 volts and negative, we've got an overall amplitude of 2 volts peak to peak there. So some of this comes down to verbiage and what particular unit we're dealing with. But I'm going to talk more in the peak-to-peak world simply because that's the one we generally talk with about. So I've got a frequency of 500 hertz coming out of this function generator. So don't worry about 3 things you need to know. This is a sine wave. It has an amplitude of 4 volts peak-to-peak, and its frequency is 500 hertz. And we're actually seeing all that on the big square here, big rectangle. We're actually seeing a 500 hertz 4 volt peak to peak square wave. Now when we look at our scope, and I realize most scopes have way more settings than volts per division and times per division, but that is the 2 that we need most to be able to calculate these values that we're seeing on the screen. So if we're at 1 volts per division, when I talk about a division, whether I'm talking about a division that goes up and down or goes left to right, I'm talking about these blue lines. Now on your scope, you probably got some small tick marks too. Those are minor divisions, but the major divisions, this is 1. So if we count total here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across, and should have the same up and down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we do. So we've got 10 major divisions each way. So we're saying each division represents 1 volt. So let's count that. 0 volts, 1 volt, 2 volts, 3 volts, and 4 volts. So 4 volts peak to peak. From the bottom peak to the top peak is where we get the term peak to peak. So 1, 2, 3, 4. And if we're just measuring a peak from the 0 line, that's where we get the 2 from that you see. Or if we're measuring a negative peak from the 0 line, we get 2. But if we're measuring peak to peak, we have 4 volts peak to peak. So that's pretty easy. Now I'm going to change how I'm viewing this. I'm going to change it to half a volt per division. Now I haven't changed the waveform. The waveform is still 4 volts peak to peak. My view of that waveform has changed. So I'm now viewing each division as half a volt. So let's count. I'm going to go to the negative peak. 1/2. 1, 1 1/2, 2, 2 1/2, 2 1/2, 3, 3 1/2, 4. Still 4 volts peak to peak. Again, it didn't change. My view changed. So I still have a 4 volt peak to peak waveform. I've just zoomed in on it for probably the best way to say that. But my volts per division changed from 1, which I'll go back to 1 volt peak to peak. So 1, 2, 3, 4, till I changed it to 1/2 a volt. So now instead of counting 1, 2, 3, 4, I have to go 1/2, 1, 1 1/2, 2, 2 1/2, 3, 3 1/2, 4. So 4 volts peak to peak. So that's amplitude. Up and down is always going to be your amplitude, and it's always going to be your voltage levels. Left to right is our period, and we know frequency is an inverse of our period. Well, we know this waveform because my function generator is putting out 5 times 100 hertz, or 500 hertz. We know this waveform is got a frequency of 500 hertz. So how do we calculate that? Well, we get the period, because remember, period is the inverse of frequency. Now, when we talk about a period of time, we're talking about for one waveform to complete. One waveform, and we have to pick a point. We can go at the peak, or we can go at the middle, or we can go at the bottom. I prefer to go to the middle. So if I start right here where my two lines intersect, my two zero lines, I'm looking for when the next waveform starts. So I'm going negative all the way, hitting the 0 line again, going positive, and I'm going back to the 0. Well, I began at the 0, and I began at the 0 where I was going to my negative peak. So I'm beginning at the 0, going to my negative peak, hitting 0 again, going to my positive peak, going back to 0. That is one complete waveform there. So again, here I would be going back to my negative, going back to my 0, going back to my positive, going back to my negative. That's another. And I've only got a half one over here. So one waveform is where we start and end up at the same place at the end of that waveform where we would be beginning another. So again, starting 0, going negative, going back to 0, going positive, going back to 0. And here we started at going negative. We're going back negative again, going to 0. So I have two full divisions here, two major divisions. So if I count from my 0 to over here, which is where the next one starts, that is 1, 2 divisions. Now my time is 1 millisecond, and we know 1 millisecond is the same as, I'm bringing up my calculator if you're wondering what happened to your screen there. We know 1 millisecond is the same as 0.001. So that's 1 times 10 to the negative third, which is 1 millisecond. Well, each division represents 1 millisecond, so this is 1 millisecond, 2 milliseconds. So I've got to multiply that times 2. So I've got 2 milliseconds. That's my period. In order to get my frequency, I have to take the inverse. Now this calculator has a reciprocal key right here, which is the inverse. When I hit 1 over x, it's 500. If your calculator doesn't have a reciprocal key, all you have to do is divide 1 by 0.002, and you'll get 500 as well. So it's the same thing. So this is telling us that the frequency of this waveform is indeed 500 hertz, 5 times 100 hertz. So we got the same value that we had when we began this video a moment ago. So we are seeing 500 hertz. Now I'm going to change the view of this for just a moment, and I'm going to go to 2 milliseconds of time. So let's again find how many divisions that one waveform is taking up. So I'm going to start at my 0 line again. And notice my wave shifted. That's fine. We're going to start at the 0 line. I'm going positive, coming down to my 0 line, going negative, coming back to my 0 line. So again, I started at the 0 line, went positive, went negative, and came back to 0. Well, I'm doing the same thing here. So now instead of having two major divisions, I have just one. So if I multiply 1 times 2 milliseconds, I now have my period. So I was able to do that just by one division. So again, we know the inverse of 2 milliseconds. If we type in 0.002, get the reciprocal, it's 500. Or if we don't have a calculator that has a reciprocal, we simply divide 1 by 0.002, and we have it, 500. So again, the value did not change of my waveform, whether we're talking amplitude, whether we're talking frequency. My view of that waveform changed by what I set these settings to. So down here, notice I'm still a sine wave, I'm still at an amplitude of 2 volts, and I'm still at 5 times 100 hertz, 500 hertz. That remains stagnant throughout this entire video. But as I manipulate these values on these knobs on my oscilloscope, my view of that waveform changed. But again, I'm back to where we began, and notice 1 volt per division. So 1, 2, 3, 4, still 4 volts peak to peak, just as we said. And it takes me, we're going to start at the middle, negative, positive, 0. Negative, positive, 0. So it takes 2 of these to give me one complete waveform. I'm at 2 times 1 millisecond, so 2 milliseconds, take the inverse of that, and we've got frequency. Just that easy. Again, an oscilloscope is a meter. The value we're measuring is fixed. The hooking an oscilloscope to it is just measuring that value. We are not modifying that value. We're modifying our look at that value. Hope that helps. As always, if you have questions, see an instructor.